Today I want to give you some quick hints just how to get started on all these. Send me emails as you have questions, and I can answer some more problems that we didn't spend enough time on. Suppose I want to find an angle between 0 and 360 degrees that's coterminal with 1200 degrees. All I have to do is keep subtracting 360 degrees till I get an angle between 360 degrees. Well, I subtract 360 once, that's not enough. 360 twice is 720. That's not enough to get an angle between 0 and 360. 1080 is 3 times 360. So I'll subtract, take 1200 minus 3 whole rotations of 360 degrees each, and I wind up with 120 degrees. There's a coterminal angle. Suppose I look at this right triangle and I want to solve each right triangle. This is one of the most important points in the course. You want to make sure you can solve right triangles. Suppose alpha is 50 and c is equal to 4, for instance. So I draw this in. Here's 50 degrees. C equals 4. Suppose I want to solve this triangle. I can solve for whatever side I want. If I call this A and B, let's see. Yeah, A opposite alpha. Then I've got, for instance, tangent 50 degrees. I'm sorry, tangent. Cosine 50 degrees is adjacent over hypotenuse. 50 over 4. It follows that B is 4 cosine 50 degrees. And you can run that on your calculator exactly. Make sure you round it to the nearest tenth. Alright. Then if I want to find A, I can use the Pythagorean theorem, or I can use trigonometry again. Pythagorean theorem is easiest. For a leg A, it's the square root of the hypotenuse squared minus the other leg squared. Whatever number you get here. Alright? And then for this angle, the last angle, beta, oops, that's just 90 minus this one. Remember the complementary angle theorem for right triangles is just 90 minus 50. It must be 40 degrees. This way, all three angles in the triangle add up to 180. Alright. Suppose I want to find the area of a circular sector. So area of a circular sector is 1/2 r squared theta. This is numbers off the page. Number 4 we're doing. A. And let's see. If r equals 3 and theta equals 20 degrees, this is just 1/2 times 3 squared. And you have to do these formulas in radians. Right, theta is 20 degrees times pi over 180 degrees, cancels the degrees, and puts it in radians, which is useless. 1/2 3 squared 20 times pi over 180 gives you the area. If I do for B, what is the arc length subtended by a circle of the same radius and central angle? Now I have arc length S equals r theta is 3 times, again it has to be in radians, 20 degrees times pi over 180 degrees. And you can multiply that out, right? So let's find the exact value of the trigonometric functions using the unit circle now. What's the cosine of 150 degrees? To find exact results, we use the unit circle for special angles. So 5a, if I want the cotangent of 150 degrees, I know that the cotangent is x over y in the unit circle. And I draw 150 degrees is 180 back up 30. So here's 150 degrees. Well, if this is 30 left, then this is a a 30, 60, 90 triangle, this must be square root of 3 over 2, opposite the 60-degree angle, 1/2 opposite the small angle, 30 degrees and 1 on this side. I infer that the cotangent x over y is square root 3 over, minus square root of 3 over 2 because it's the coordinates, not the distance. So the coordinates are minus square root of 3 over 2 1/2. So it's minus square root of 3 over 2 over 1/2 is minus the square root of 3. There's the cotangent of 150 degrees exactly. Suppose I want to find the angular speed in radians per second if an object's rotating at linear speed 12 feet per second along a circle of radius 5 feet. Right? So there's number 6. The angular speed, omega, is related to the linear velocity v by v equals r omega. You remember that formula? It's just this one, s equals r theta divided by t time. Theta over t is the angular velocity, s over t is the linear velocity. So you take this one, divide by t, and get this one to call. Now we're given that the linear speed is 12, and the circle radius is 5 feet, so omega must be 12 fifths. We could do that kind of thing. Sketch the graph of each function. How about that? Suppose we try one of those. Let's try 7a, y equals minus cosine 2x plus 3 over 1 period. Get your calculator out afterwards and check to make sure your graph looks correct. But on your graph, I want to see some exact points, so don't just use your calculator. So we're going to figure out, this is a y equals a cosine bx plus c plus k. So here's a, b, or plus d, c and d. And we now say that the amplitude is the absolute value of a, is 1. The period is 2 pi over b is pi, assuming b is positive. The phase shift is minus c over b is minus 3/2. And the vertical shift is d is nothing. And finally, is there a flip? If a is negative, there is. Yes, a is negative. It's flipped upside down. So now we can sketch it. We do a vertical shift of 0, a horizontal shift of minus 3/2, and the center of the graph is at minus 3/2, 0. Now we can draw the asymptotes, plus and minus the amplitude from there. 1 unit above at 1 and 1 unit below at minus 1. The cosine starts at the top if it's unflipped, at the bottom if it's flipped. So we're going to start down here, and then 1 period is pi, so we're going to go to minus 3/2 plus pi, which is right here, and complete 1 period. So what I want to do then is draw this up and back down like that. And if you want, you can plot some important points like, what is this peak? Well, it's halfway between these two, so it's minus 3/2 plus a 1/2 pi, right? Half the period from here, halfway between here and here. Since period pi, go half the pi. And then it's at the top, so the second coordinate is 1. And you can find these crossing points by adding a 1/4 pi and 3/4 pi. All right. Suppose I want to solve the trigonometric equation for all angles theta. Let's try this one. This is kind of hard, 8a. Cosine 2 theta plus sine squared theta minus a 4th equals 0. Well, our first hint is to get one angle. So I've got an angle theta and an angle 2 theta. Get rid of that. Let's replace cosine 2 theta with cosine squared theta minus sine squared theta. Now we'll have one angle. And it's so much easier, right? Because in this case, it happens the signs cancel. I get cosine squared minus a fourth equals 0. You put cosine squared equals a fourth and put cosine as plus or minus square root of fourth if you want using square roots. I'm going to do it this way. I'm going to factor cosine squared minus a fourth as cosine minus a half times cosine plus a half. It might behoove you to think of this as u squared minus a fourth equals 0. And so it's u minus a half times u plus a half equals 0 by factoring, and then put back u equals cosine theta. So this is it. Now I know that cosine theta equals a half, or cosine theta equals minus a half. Once I have trig function equal a number, I can solve that on a unit circle. So cosine theta is the x coordinate. So I put x equals a half, that vertical line, and x equals minus a half. I observe that there's 4 rays. 1, 2, 3, 4. And if I'm supposed to solve this for all theta, then I'll say I have to add 2k pi to each of these 4 angles. So the first one here, if x is a half, that's this side, then this side is 1. The last side has to be square root 3 over 2 by the Pythagorean theorem, actually. And so this is a 60-degree angle. One angle theta, did I say radians? Yeah, radians. 60 degrees is pi over 3. Similarly, by symmetry, this has to be pi over 3, so this must be 2 pi over 3, so they add up to pi. 2 pi over 3. And then pi plus pi over 3 makes 4 pi over 3. This angle, this one, and this one are all pi over 3 by symmetry. And 2 pi back up pi over 3 gives me 5 pi over 3 for the last one. And then each of these plus 2k pi to get all solutions. Infinite number of solutions. There they are. Alright, suppose I want to find a trig function of an inverse trig function. Remember how to do those? Those are tricky. If I want to calculate on number 9a, the cosine of the arctangent of 0.4. Well, I might just for convenience write this as any fractions I want. Let's call it 4/10. And we'll say, when you have a trig function of an inverse trig function, you draw a triangle with theta equal with the inverse trig function that you see. So theta equals arctangent of 4/10. So that means that tangent theta equals 4/10, which means that I can make a right triangle with y equals 4 and x equals 10, and the tangent of this angle will be 4/10. This angle must be the arctangent of 4/10. This side that remains has to be the square root of this squared plus this squared. Is the square root of 116. Is also 2 square root 29, I guess. So we now want to say the cosine of the arctangent of 0.4 is the cosine of theta, because I made theta that way. The cosine of theta is the adjacent over the hypotenuse, is 10 over 2 square root 10.9. Is 5 over square root 29. If you don't want your algebra teacher to roll over in his or her grade, then you rationalize it. 5 square root 29 over 29 for the final answer. Alright. Now, here's some triangles that are not right triangles. I have to ask you that on this test too, because I didn't get to on the previous test. Whenever I do a triangle is not a right triangle, this is a law of sines or a law of cosines. And you have to think about what you're given. Alpha, gamma, and c. Now let's just draw this. Here's something like a 20-degree angle. That's alpha. Gamma is 50 degrees. That's pretty close to 45 degrees, so maybe it looks like that. A little over half a right angle. Gamma equals 50 degrees. They don't have to be real precise, but if they're sort of close, they'll sometimes keep you from blundering, right? And then opposite gamma is C, so this must be 2.0 over here. Now look what I have. I have an angle, followed by an angle, followed by a side given. Do I use law of sines or law of cosines? For angle, angle, side, I use law of sines. Alright, so if I use the law of sines, then I want to use an angle on its opposite side, and I'll say sine of 50 degrees is to 2.0 as, let's see, 20 degrees was alpha, so this is A, and this is B and beta, as sine 20 degrees is to its opposite side, A. So the side of each angle is its opposite side as the sine of any other angle is to its opposite side. This is what I have. I can cross multiply or I can take reciprocals, it doesn't matter. Let's cross multiply and say this one times this one equals this one times this one. Divide by sine 50 degrees and get A equals 2 sine 20 degrees over sine 50 degrees gives me the last side A. Let's see, the next side A. I still need to find B. Don't use the Pythagorean theorem at this point because it's not a right triangle, it doesn't apply. Let's erase this. Now I've got two angles, so I can find the third one immediately. Gamma is 180 minus 20 minus 50. Is 110 degrees. And if I apply the law of sines again, I'll say sine of 110 degrees is to C as, let's go back to the original data, sine, oops, is to, sine gamma, this is beta. Sine beta is to B as sine gamma, 50 degrees, is to C, which is 2.0. Now you're supposed to round all these things to two significant digits if it doesn't say otherwise, since they're all given to two significant digits. So what we'll do here is, from algebra, calculate that B equals 2.0 sine 110 degrees all over sine 50. Gives me the last side, and I'll round it to two significant digits. There's how to solve the triangle. This is using the law of sines in the angle-angle side case. Be able to do all the different kinds, not just angle-angle side case. How about problem D here? Suppose I told you A equals 8, B equals 5, alpha equals 35 degrees. Now what have I got? Well, I can draw a base. Here's maybe a side of 8. Here's maybe a side of 5. And maybe here's an angle of 35 degrees. This is A, B, and alpha opposite A. Now what I notice is I have side, side, angle. So it's a law of sines again. Now what I'm going to do is I use the opposite angle and side that I'm given, sine 35 is to 8. And the other one I know, I'm trying to get 3 of the 4 quantities in the law of sines known as sine of beta is to 5. Right? Well, this says that sine beta is 5 sine 35 degrees over 8, which you can solve for. Take just a second here to change the mode. Alright, so 5 times sine 35 degrees divided by 8. Make sure you close your parentheses on here on your calculator. Gives me, let's see. .36 approximately. Now I can evaluate beta either by taking the inverse sine or maybe it's 180 minus the inverse sine. Which can it be? Well, it could be either in the side-side angle case. So we try beta equals the arc sine of 0.36. I'm going to carry more digits. I'll just put arc sine and answer. So I'll take inverse sine, answer, and get 21.0 something degrees. So approximately 21.0 degrees for beta. Or beta could be 180 minus the arc sine is 159 degrees. And then you have to make two triangles, one with each of those angles, because in general they both work. Sometimes they don't both work. In this case, if beta is 159 degrees, you observe immediately that you can't have another 35 degrees. You get more than 180 in the triangle, so this one's out in this case. In this side-side angle case, there's only one triangle. You can get 0, 1, or 2 solutions in the side-side angle case. How could we have known that earlier? Since B is the shortest side, beta opposite has to be an acute angle, and right, only one angle at most can be obtuse in a triangle, bigger than 90 degrees. So once I knew that beta had to be acute, I didn't have to check this case at all, actually. Now I've got beta equals 21 degrees, and alpha equals 35 degrees, so gamma is 180 minus 35 degrees minus 21 degrees. Is 124 degrees. That's the last angle. Now you can use the law of sines one last time to get the last side. You can't use the Pythagorean theorem, recall. So I'll use sine. Let's say I need A still, right? No, I need C still. So sine gamma, which was 124 divided by C. divide by c is equal to sine alpha over a, sine 35 degrees over 8. Find c. So there's how to do the side angle case. Well, we haven't done any polar coordinates yet. Let's find the polar coordinates at this point. What you do is you turn through the angle and then see how far you move out. This angle looks like 30, 60, 90, 120. So theta equals 120 degrees, or we can call that 2 pi over 3 in radians. And r, along this ray, I moved out 1, 2, 3 units, so r equals 3. Evidently, I plotted the point 3, 2 pi over 3. It's r followed by theta always. All right. Here's one that we didn't talk about a whole lot. Let's make sure we look at this one. What's the angular frequency, and period of this one? If you have y equals 6 cosine pi x, what you do is you recognize this is 6 sine or cosine, or a sine or cosine, cosine b x plus c plus d. Alright? And so a is 6, b is pi, c is 0, d is 0. And now what's the angular frequency is the easiest one. Angular frequency is just b always. Just read it off. It is pi. Now the frequency is the angular frequency over 2 pi. Is a half. And then the period is either 1 over the frequency or it's 2 pi over the angular frequency. Is 2. So this has period 2, frequency 1/2, and angular frequency pi. Let's take a look at a few of these. Suppose I want to convert an equation from rectangular coordinates to polar coordinates. You just have to know these things, that the conversion is x equals r cosine theta, y equals r sine theta to convert any polar coordinates to rectangular. X squared plus y squared equals r squared, and tangent theta equals y over x to convert. Let's write it this way. R squared equals x squared plus y squared. Tangent theta equals y over x to convert rectangular coordinates to polar. You can also use those to convert polar equations. You can replace x everywhere in here with r cosine theta and y with r sine theta, and that works. But what's easier than just putting in for x and putting in for y, when you see an x squared plus y squared in an equation, immediately replace it with r squared. So this is r squared equals 8, and then over here where you just see x, we'll just replace it directly, r cosine theta. So there's the equation for the curve and polar coordinates, completely equivalent. Now I notice, however, that if there's a common factor of r, I can divide through by r and write this is actually r equals 8 cosine theta. It's convenient in higher mathematics to write r as a function of theta if you can. So let's do that here. There is one thing you have to be careful about dividing through by r. R equals 0 is a solution here. That's the pole, right? That's the origin in the xy coordinate system. Is the origin a solution here? If I divide, it is a solution here, r equals 0. Is this origin r equals 0 still a solution? Well, not for all the same values of theta, but it is a solution. If I put theta equals pi over 2, I can get 0 on this side equals 0 on this side. So the pole is still a solution. We didn't lose it when we divided through by r. Remember, you can divide any equation by a non-zero number. In this equation, 0 and 1 are both solutions, but if I divide through by x, I get x equals 1. I've lost the x equals 0 solution. You're doing the same thing here, just being careful. Did I lose the zero solution? You lost it for somebody of theta, but r equals 0 is still a solution. That point, all points with r equals 0 is the pole, and you still have the polar solution here. So this is the best way to write the equation. Finally, I want you to be able to do applied problems there with a picture. This is a classic example. I'd love to put this one on the final. Suppose I have two observers, one here and one here, and they look to the top of this building and they want to see how high it is. This is what's actually used in lots of cases to find heights of things. For instance, you want to find a height of a mountain without scaling it, or you're looking at the Nazi aircraft coming in, you want to know how high they are. If you know how far apart your boats are and you measure the angle up from each, you can tell how high to shoot the flak or something, right? So this is a useful problem. If I have 18 degrees, looks like more than that, doesn't it? It's not scaled the same on the axis apparently. 25 degrees, and that goes up to a tall building, and I want to find the height h. Put in everything you know, and 1,000 here, and the thing you don't know, and then try and solve for it. Well, how can I solve for that? I've got a problem. In order to solve an oblique triangle like that, I need three pieces of information other than angle, 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 which is a congruence theorem. And I only have two. I have this side and this angle. Same thing over here. I have actually only one angle. What you first do is put in anything you can figure out from the diagram. This is why the diagram is so important. If this is 25 degrees, these two angles are supplementary. This angle must be 180 minus 25, right? So it's 155, I deduce immediately. Once I know that angle, now the sum of the three angles is 180 degrees. I know this angle. This is 180 minus 18 minus 155, right? This one plus this one plus this one has to add up to 180. Is 7 degrees. So this is a 7-degree angle here. And now I know angle, angle, side. I have the law of sines to solve this triangle. So I apply the law of sines, and maybe I want to find this side here, C. Let's do this one. Actually, let's do this one. To find C, I can use its opposite angle. This is what I need, is an angle on the side I want to find, and an angle on the side that I both know. I'll say sine of 155 degrees is to its opposite side 1,000, as sine of 7 degrees is to the side I know, 1,000. And now I know everything. Put it this way. Sine 155. It's not to 1,000. It's opposite side. I guess I'm calling this. Should be sine 18 degrees is to, should not this way. Sine 18 degrees is to its opposite side C. And sine 7 degrees is its opposite side 1,000. Sorry about that. So that I have three knowns and one unknown, and I can solve for that unknown. Well, if I cross multiply, I've got 1,000 sine 18 equals C sine 7. Divide by sine 7, I get C equals 1,000 sine 18 over sine 7. Now I know C in a right triangle. If I know it's a right triangle, assuming the building is straight up, then if I just need two pieces of information, an angle and a side, or two sides, I can't take the two angles. That's like knowing one thing. Once I know one, I know the other. So that's what I have. I have a side and an angle. I can solve this right triangle now. So what's the right triangle relationship that relates to side C that I know? This angle and the side I want to know. Well, let's see. The sine of this angle is h over c. So sine, I'll put in that's the sine of 25 degrees is equal to h, what I want to know, over the sine I just found here. Maybe I should run this one. I have c equals 18, b equals 15, a equals 10. I write down one of the law of cosines things. C squared equals a squared plus b squared. squared minus 2ab cosine gamma, for instance. And I can use that to find gamma. So I've got 18 squared equals 10 squared plus 15 squared minus 2 times 10 times 15 cosine gamma. Well, 2 times 10 times 15 is 300. And let's see, I can take now 18 squared minus 10 squared minus 15 squared equals 300 cosine gamma. Minus 300 cosine gamma. And divide by minus 300 and get 18 squared minus 10 squared minus 15 squared all over minus 300 equals cosine gamma. Then gamma has to be the inverse cosine of this. Remember, there is no ambiguous case with the law of cosine, so gamma is the inverse cosine of whatever this number is. Unless, you better check it, the sum of two sides is bigger than the other side, so it's not a possible triangle. The sum of the two smallest sides is 25 is bigger than this one. If these aren't at least as big as the longest side, then there's an impossible triangle, right? So let's run this, and I'll try arc cosine of 18 squared minus 10 squared minus 15 squared divided by minus 300 Okay, gives 89.8. It's almost a right triangle. You could have treated this as a right triangle. How about that? Now you can go ahead and finish the rest of the triangle. Once you have the law of cosine set solved, you can apply the law of sines of the next step. So now what I'll do is say the sine of 89.8 degrees is to C as, and I'll take the smaller of the two sides remaining, let's say C was 18. Oh, actually, it doesn't matter. So sine alpha is to A, which is 10. Well, the point is to pick an angle here that's not opposite the largest side. The angle opposite the larger side might be obtuse, and then you have the ambiguity in the law of sines. So I picked the smallest side here, 10. I know the angle opposite it will be acute. So let's see, now alpha is the arc sine, multiply by 10 and take the arc sine. Alpha is the arc sine of 10 sine 89.8 over 18. And you can carry that out, and then once you have that, gamma, let's see, not gamma, we have theta will then be 180 minus what we found for gamma minus what we find for alpha here. We'll get the last angle.